right, there we go. So what we're going to look at today is Fusion 360's version of the, they don't call it Topology Optimization, SolidWorks calls it that, but the same kind of thing. So it's another one of those deals where I had to run the simulation beforehand. This one doesn't run locally, it runs in the cloud, but still it takes a long time. Actually, this, I don't even know how long this, I just let it run overnight. I'm not sure it tells me how long it took. But I basically set up the same thing. I'll go through the building the model part again, just because that part's interesting and it doesn't take a long time to do. And this one actually runs several, or it can run several types of solutions at one time. So you can ask it to, well, what if I want this material? What if I want that material? What if I want this machining process or additive? What if I want to print it in this direction or that direction? So it asks you several different ways that you might want to simulate this thing. So let's look at that first, and then we'll assume we'll have some time left at the end, and I've got some filament options over here that we'll look through. I did get the green transparent TPU stuff to print, although I haven't got it to print very well yet, so I don't know if it's old and full of moisture or if I just don't have the settings right yet, but we'll look at it. I did get it to print, it's just not right. So let's go over to Fusion 360. Fusion 360, if you haven't used that before, it's Autodesk Fusion 360, so they own this product, and it's similar to SolidWorks in that it does a lot of the same things and it models more or less the same way. It does have some features that SolidWorks doesn't have, and I'm sure SolidWorks has features it doesn't have. It's another one of those that you can get a free version that's kind of stripped. I guess it's not stripped down, but some parts are locked behind paywall type stuff. Now, if you have the education license, so you can see mine education license, which as far as I know, you just need an email that ends in .edu, then it's pretty much open to do all of it. In fact, Autodesk has a lot of products that you can use totally free for educational purposes. Now, if you don't want to start commercializing things and using them, then they cost. But to get started, you can use most all of their stuff for free. There might be a few things that aren't free, but most all of them have completely free versions. So what we've got over here is the result. I ask it to do basically two different studies with different materials. Now it says the solver could not achieve the objectives. I actually don't even remember what the objectives were. Probably a weight reduction type thing, although I don't remember telling it a particular weight reduction. But we'll look at what it came up with. The two different materials I asked it to use were an aluminum, so you can 3D print some aluminum, and a Orgasol Invent Smooth PA12. So that's a nylon, PA's nylon. So it's a nylon 3D printable, probably through a SLA type process. So like I assume, I don't know what Orgasol Invent Smooth actually goes with, what machine it goes with, but I'm assuming it's a SLA type printer that does nylon. Most of these are assuming you're using some sort of resin SLA. SLA is selective laser apparatus. So you're using a laser to cure resin. And that's usually what they're assuming you're doing. They're usually not assuming that this is going to be printed in a FDM style print. But you can still print them that way. They just are not necessarily going to have this quite same strength because they're not going to be as isomorphic of a material. Now I do have a material over here that we'll look at later today that can kind of do that and still be FDM. But anyway, let's look at this stuff. So I don't know which one of these is which, outcome 1 and outcome 2. They actually both look pretty much the same, and they both failed as far as it goes. But what you can do here that you can't do in SolidWorks is, let's look at one of them. And so this is the aluminum. Manufacturing method, additive, orientation. Let's see. Make sure I'm actually connected here. It says I am on the streaming side, so I'm not sure. Maybe it's just because I'm streaming that it has less resources. So here's what it actually came up with. Like, you can see this big triangle here. That's because I told it to print it this way. like this, where the bed's down at the bottom. It would have been better to print this way, clearly, because what it ended up having to do is put most of the material down here to be able to print it. But that's the way I set it up, and I don't want to rerun it. But the thing you can do is you can go through this slider at the bottom. It took 34 iterations, and you can go back in time to any of them and look at, well, maybe, assuming your network connection is okay, you can go back in time. You can kind of see down at the bottom on the slider, if it won't load it, you can see the different, here it is in this picture up here, different iterations. It's just being slow, I assume, because I've got too many things consuming bandwidth right now. But you can see it how it had something that looked a little more realistic. And the thumbnail for this picture is actually one of the ones, or thumbnail for this video, is one of the processes in between. One of the, I don't remember, I think this was step 30 or 31. I think this was 30, which is the one I was trying to load. But you can kind of see where it was headed. So what it does, if we look at the bottom of the screen down here, since it's not going to do there, you can kind of see previews. And let's go to the beginning. So basically it starts out with more or less what we started well in SOLIDWORKS, although I didn't create this geometry. Well, it's going to try and load that one now. I didn't create that. I created, well, there it is. It'll load that one. So I created basically this top surface and this back surface. And then it filled in basically just, you know, the volume between those. It started with that. So it's a little bit different on the setup side of things. And then it goes in and sort of does what SOLIDWORKS does. But they call it generative because you didn't create all of this in the middle. It generated that. Whereas SOLIDWORKS, you create all of that to start with. And then SOLIDWORKS optimizes it. So they do topology optimization. Fusion 360 does generative design. But in the end, they're basically the same thing. There are a couple of different ways that they each have like little details about them. Once we start setting one of these up, we'll look at that. So that one's not very interesting, but let's scroll through. Then you can kind of see down here at the iterations at the bottom of the screen how it's eating away at the different materials. And so you can, at any point, you can get to a point where like, I like that one. And then if it would load up, which maybe it will now. We'll see. We'll give it a few seconds to see if it'll load. There it is. I like that one. Now you've got this, you know, I'm on iteration 30. I don't go all the way to 34. It apparently doesn't succeed at this point. You know, it didn't meet one of the goals, whatever that might be. But it has a minimum factor of safety of 14.5, so it's okay. It's got 16 megapascals of stress, so that's not a lot at all. And what you can do is you have two options here in the create. You can create a design from this, or you can create a mesh from this, and you can go modify directly the mesh or the design. I didn't click on these because I'm not sure how long it's going to take to do. I'll pick one and we'll do that just to see how quick it does. I'm going to assume the mesh is actually pretty fast to do. And the design is a little bit longer, but let's see. It's preparing it. So usually when this pops up, it is doing this in the cloud. And you may or may not have to pay for that part. As far as I know, on the education licenses, they're free, unlimited cloud access for any of the stuff that Fusion 360 does in the cloud versus locally. I'll let this go for a little while. Again, when it was doing the actual generative design part, I don't know how long it took. It took, you know, overnight. Let's see if it gives me anything about details here. It doesn't tell me how long it took to run these. I'm sure it tells me somewhere. I just don't know where. Processing status completed. Nope, that's not what I want. Yeah, I'm sure it tells me somewhere the time, but I don't know where to easily find that. So we'll ignore that part for now. But I let it run overnight. I know that I let it run for probably about an hour that I was seeing it run, and then it hadn't got anywhere near here. It was still like on iteration, I don't know, 5 or something. So it did take significantly long period of time for it to solve. So how do you get to this point? Let's do that. Let's close this. That's the little part navigator where your parts are stored. Again, your parts are generally stored in the cloud. You can download them locally if you want to or need to, but they're generally in the cloud. I'm going to finish. Let's see. No, let's just start a new one. That'll just kind of sit there in the background. It's not doing anything. Start a new design. Oh, there was the thing I actually designed. All right, so how this one works is you design in parts that you want to, like, they're important. So like the top of our little shelf bracket, that's important. Where it mounts to the wall, that's important. You can also design in things like that you cannot put any material here. There's a wheel there, or there needs to be a bolt there, or whatever. So you can have blockers that make sure that it doesn't generate any material in that particular location. You can do that also. So all I did though is I sketched out. Let's do units of inches, because I did the other one in inches. I won't set it as the default though. All right, so let's grab the center point there. And I made this 8 inches on the one that we did in SolidWorks. Oh, didn't want to do that. They did have different shortcut keys between them, so I don't remember, or I get confused on which one I'm doing sometimes. Let's see, I made that 5, 6. I think I made that 6 inches, maybe up. All right, so that's all we need for that part. So this is going to be the little top shelf. So I'm going to extrude that guy in both directions symmetrically, and I wanted that to be. Oh, so that's the. I made that 1 inch and then 1/4 inch on either side, kind of overhanging the thing. So I think the whole thing ended up being 1.5 inches. So I need to extrude in both directions 0.75 inches. So there's our little top part. Now let's create the side part over here. Something like that. Make that about 5. That 1/4 inch. And then we'll extrude that also. Fusion 360 does take on a little bit more of a direct modeling approach than SolidWorks does. I mean, you can do direct modeling in SolidWorks. By direct modeling, I mean like you can go and grab faces and push and pull them and change dimensions like that. You can do that in SolidWorks also. It's a little bit more built into the system in Fusion 360, whereas SolidWorks kind of has added that over the years. Let's see, I need to do a symmetric. This one was only 1 inch thick, so 1/2 inch on either side. So there's that plate. So there's the plate that's going to mount it to the wall, and there's the one that's going to be the top of the shelf bracket. I did put some holes in here, so let's put those. There is a hole, create holes. I'm just going to create a sketch and subtract them out. And we'll do, I think I did, not 1/2 inch, I think I did 1/4 inch diameter holes. I don't actually remember that part, but I think that's what it was. And then I placed them, I think 2 inches apart. All right, and we will extrude those guys. Through there. Oops. Nope. I extruded in the wrong way. There. All right, so that's all there is. Now we could build in more geometry that we want to have for certain. Usually you build in like the interface points where this part has to interface with another part. So you usually build those in. And then you might also build in some places where I cannot have material show up in these locations. Like for instance, you might want to get to these bolt holes. You might want to make sure that they're clear. And so you could go in and build some support blockers. Not well, they're kind of like support blockers, but material blockers in front of those. So maybe, I don't know, something like, I don't want to connect them to that part though. Something like that, maybe. I don't know. Maybe that's too wide. That's probably too wide. The hole was only a 1/4 inch, so let's make this a 1/2 inch. And let's drag it all the way out there and kind of center it up. So now it won't put any material right there. And then we'll extrude this in both directions. 1/4 inch. Oh, not two sides symmetric. Two sides is if you want them to be different direction. You know, one side 1/4 inch, another side 1/2 inch or something. So now I've got this little thing. I didn't want to connect it to this surface. There's probably a better way to not do this, but if you connect it, then they become one part, and I need two separate bodies. So we could make all those that we wanted if we wanted to have those in there. All right. So I also noticed that I may not have the most recent version of Fusion 360 up to date, because the newer stuff has a plastics tab up here for plastic modeling. I don't think it's over here. No. So I want to look at that, because what it looked like is that the new plastic modeling stuff is similar to how you can model in sheet metal with SolidWorks, or if you've done Fusion 360, you could model in there. And where it has particular tools for sheet metal folding and all that. I saw that there were some particular tools for plastic modeling that build like screw bosses and snap fit type things. So I wanted to try those out and see how well they worked with 3D printed versions of those things. It's assuming you're going to mold those, injection mold, but it could work also with 3D printing. So I'll have to see if I just need to update my Fusion 360 or whatever to get that plastic modeling tab in here, because I don't see it. I see sheet metal, but there's also a plastics one that I saw that's recently been added. So I need to add that. That might be what this notification is, that I'm not up to date. So we won't do that right now. In fact, I don't know how to use it anyway. So once I figure it out, then I might, if it's good for 3D printing, I might add it into the stuff we talk about. So here's my model. It doesn't look like anything, but that's what I'm starting with. And I switch over to Generative Design. They've got render, animate, simulation. That's their FEA type stuff. They do keep their Generative Design out of the simulation tab, although it's doing a lot of the same things. It's doing them in a totally different way. So let's go over to Generative Design, and as you can see, my toolbar changes up here, and I'm going to first, you can edit and you can set up a new study here. I just created a new one, so I don't need another new one. So I'm going to go, I don't want to edit anything right now. If I already had created a model, I could edit it here instead of I just created it as a model to be done. So here's where you really start the way I've approached it. So you have to preserve some geometry. Those are your interface points. So you basically click bodies you want to preserve. So I want those two things to be preserved. Like they need to appear in whatever the final design looks like. Obstacle geometry, if there's any places you need to avoid. So that's this little guy. I don't want any material to be generated in that area, in that volume. I guess it's a volume, not an area, that is red. There's also, you can have a starting shape. So if you have a particular shape that you want it to start from, that's more like what SolidWorks does. So if you could do this exactly the way SolidWorks does it, where you create a starting shape. It does have to be able to also have some geometry you preserve that's separate from the starting shape, as far as I remember. You can do obstacle offset, so you could have created this just as an offset, like you want to have clearance around a certain place. This will be fine. So now that's what our design looks like so far. I did not put this red obstacle in the one that I generated over here. So there's no red obstacle. I wonder if it finished our, we'll have to come back to that and see if it finished solving our design, exporting it. So here are your constraints. So you have fixed constraints, pins, and frictionless. So you don't have as many of the types, you know, bearings and everything, but everything can kind of be summed up in these three. You know, that's, if you're thinking about statics and mechanics and materials, you kind of have fixed supports, stuff's welded to a wall or embedded in the ground. You've got pins and you've got rollers, and that's kind of how you summarize most of the things. It falls into one of these categories. SolidWorks has some very specific ones that are specific examples of these three things that, you know, may make it a little bit more specific. I use specific a lot. It may make it a little bit more particular to that design, where you can go in and you know, have a bearing fixture and apply a certain friction to it or whatever. These are a little bit more generic. I'm just going to do fix in all three directions, and I'm going to fix these bolt holes because I don't want them to move. So that should hold it in place. We can also add structural loads, or we can do, you can edit the attributes of the load, but I'm just going to put a force on this top surface here. And I will put it in pounds. I don't remember what pound force we ended up using last time. I believe it was 50 pounds maybe. I might have dropped it down to 25 pounds. I don't remember. Let's use 30. I'm not going to run this simulation, I don't think, anyway. But we'll put some numbers similar. Maybe I'll run it, I don't know. All right, and then you've got this design criteria. So what are your objectives, and what are the ways that you want to consider manufacturing this thing? So the objectives here are also a little bit simpler. I think I put a safety factor of 1.5, although it ended up with nearly 15. And you can either minimize mass or maximize stiffness. So I believe I put it on minimize mass, which is why it came down with just this little thin bar in the end. We can also specify, well, what different ways do you want to manufacture this? So unrestricted, it'll just consider all the things it knows about. So I usually don't do that because it'll generate a bunch of different options that I may not be interested in. So there's additive. It can also do 2D milling. There's a 2-axis cutting like laser jet or laser cutting or water jet cutting. Die casting, so you're kind of some molding stuff. So there's several different things that have constraints on them. Like if I'm doing a milling operation, then I can't cut and undercut in a 2D mill. If I'm doing water jet, then I basically just have a pattern, you know. So it kind of gives you a preview of, well, the others gave you a preview of the picture. This one just gives you words. Or if I'm doing a mold of some sort, then I've got to think about draft angles and being able to remove the part from the die. So I just clicked on additive, but in additive, there's a bunch of different direct orientations that this part might be in the printer. So which way are you going to think about putting it in the printer? I put it in this way, which is why it generated the solution that it did. You know, it might make more sense this way. So looking over here, that is the negative Y direction. Y is pointing down. And you can click them all if you wanted to, you know, it'll generate all of them. And it doesn't necessarily take any longer time because it's all parallel happening in the cloud. And overhang angle, you know, what is your printer capable of doing without supports? Even resin type printers will sometimes need support in them. The only ones that don't need any amount of support are the powder-based printers, where the powder itself just doesn't get cured, but it's still there and it holds the part in place. What's your minimum thickness for stuff? 3 millimeters. That's certainly large enough for any kind of printing. And we'll click OK on that. Materials. What materials do you want to consider this thing being made from? So it's got this aluminum. Let's look at just the additive process. There are metals. that can be 3D printed in a selective laser sintering type setup or direct metal printing. And then there's a couple of plastics that there's one for the HP Fusion Jet. So these are all commercial level printers. They're not going to have like PLA on your Ender 3 here, at least not yet. Maybe someday they'll figure out how to model that. But the interlayer adhesion is so much weaker compared to any of the other directions that it's going to be a tough thing to model, or at least it's going to be more complicated than assuming it's basically a solid. So I picked that one. So you just drag it up there to your options. You can get rid of one if you don't want that one. And then you can go through, you can do a little pre-check. It'll tell me that I don't have, oh, it has everything. Sometimes it says you don't have a, if you don't have the starting shape. The starting shape is optional. Sometimes it'll give you a warning that, hey, you don't have a starting shape. Do you want one? You can even do a little preview here that will basically show you what iteration 1 is going to look like. So, and it takes, I don't know, a minute or two to run. This one runs locally, so it is dependent on your processor. As a aside on running these kind of things locally, if you're on a laptop and you want to do some of these heavier duty processes, you probably should plug the power in. Don't run on battery. Most laptops, unless you go in and change it, are going to run at half processor speed when they're not plugged in, just to save battery life. So if you're on a laptop trying to run one of these, plug it in. See what I can do. What if I do medium detail level? See what that does. That was low detail level. So it'll give you an idea of where it's going to go with this. And you can actually see it. You know, there's the initial one. There's a refinement of it. And then it'll do a couple of, I don't know how many steps it's going to do at the medium. I don't know if I want to do the high detail though. And you can kind of see inside there where it's avoiding this red obstacle. It's not putting any material there. It's making sure to keep that. I didn't do one for the bottom here, but it would, if you wanted to keep that hole clear, then you could put one of something like this in front of it also. So it'll give you some ideas of like, yeah, that's kind of what I want. Now it's going to, apparently it's going to put these large bulges on the back over here, which you're going to have to cut those off. Because we didn't put a blocker back there to keep that surface flat. But you can kind of see how it went around the blocker there. And you can say, okay, we can go with that. Then you go to, we can stop the previewer. You go to Generate. And over here is, it will tell you how much it's going to cost. So it would cost 11 cloud credits. If you have a .edu educational license account, you currently, I don't know how long this is going to last, but it's been this way for years now. The educational licenses have unlimited uses. It's a real cost to Autodesk to rent out the Amazon server and run these things on that cloud, but they still allow free use for educational licenses. You're not supposed to use the results from that in any commercial way, though. So this would take 11 cloud credits. I don't remember. At one time, I think a cloud credit might have been like $10, maybe. I don't remember for a single one. So this might be $100 or so. I don't know the current exchange rate for cloud credits, and I'm not even sure how to buy them. I think if you go to this Manage Cloud Credits, you can go in and buy them, but I don't need any. And so you would generate one study, and that would send it off to, I might as well do that. It's not going to do it anytime soon, but we can look at it, the process of what it does. There we go. And then it will send it away. Oh, look, our design is complete. We can open our design from our other one. So these are kind of all your jobs that are running in the cloud. I don't have any data jobs. I don't have any simulations that are running currently. And you can go and view this. Okay, that's just saying it's going to give me some previews once they get it done. And you can look at these things. I want to open this design that we told it to generate. So there's a model that I can, now I can edit this model if I wanted to do some editing to it. I'd have to use the form editing, the mesh editing over here, I believe would be the best way to edit it. Or I could use it as a template to design a new thing or whatever. That's a little bit beyond the scope of what we're trying to do today, because now we have to get into, well, how does all this stuff work? But we could do some of that. I'm not super good at that, but you can definitely tell that you don't want these. I think it will let me just, oh, well, maybe it won't let me do it that way. I wanted to just delete these faces, but it doesn't want me to do that. So there's something I need to do first. Maybe I need to, I don't remember. Direct edit is what I want to do. I don't remember the details of how to go in there and work on these meshes. I can look that up and work on that later. But that is, I do like this feature that you can kind of scroll through the iterations that it went through, and then you can take, oh, I made this as a body. I didn't make it as a mesh. So the other option was to create a mesh from there. That probably would have been what I needed to do, is create a mesh if I wanted to do these mesh tools. I actually created this as a body that I could build off of and refine or whatever. So it might have actually been better to generate this as a mesh if I want to do all of this stuff to it. I think you can convert them. I don't remember the details on how to convert them. Maybe there's a surface. I wonder. Yeah, I think it's as a design body right now. Like, I can select the whole thing. So I think it's a design body. All right. So this little guy that we sent off, it's going to take, I don't know how long before we get our first preview back. It's probably going to be 20 minutes or something. And the first preview is just going to be that triangular shaped block with a hole through it for the blocker that we put in there. But this will run for hours now, and we'll get some data back much later. But that's kind of how Fusion 360 does their generative design. Oh, okay, that's what that symbol means. All right, so I'm going to finish exploring that one. We're going to, this is the one that we just did. You can save them over here. They appear in your little work folder over here. I think they're alphabetical currently. At least that's how I have them listed. So I don't remember what I called it. I think I called it summer. Yeah, there they are. And so you can go back and edit them or whatever. All right. So I think we'll close this guy down. Let's save this one. Maybe I can come back and okay. Now it'll be right there. All right, I'm going to close down this, and we've got a few minutes. We can look at some of these materials. This will keep running in the cloud. I don't need to keep that open for it to do that. All right, so now we'll free up some resources here. Hopefully. There we go. All right, so let's go over to here. So here are we've tried printing the green TPU. And I did manage to get it to print twice, but you can see, like, they're not very good prints. Let's see if we can make them a little more in focus. You can see how stringy the tops of them are. They are flexible, like they're squishy. This one I printed a little bit hotter, and I think that actually might have not helped. So this one is the first one. Then I put the filament in the dryer for a couple of hours, and it started printing better. Like this first part here was okay. It's not horrible. And then I raised the temperature and it got a little worse, maybe. It's bonded better, but I think it's actually a worse print. And then this usually looks like there's some heat creep, like the nozzle's getting clogged up here, where it gets really stringy up there. So I might try printing again. First I might try leaving the filament in the dryer longer, because I don't know how old that filament is. You know, these are filament that just come in little sample bags that I get, and who knows, I mean, they're not sealed. Sometimes they have a little piece of desiccant in there, but you know, they're just in a Ziploc bag. And TPU is a filament that is typically bad at absorbing moisture, or it's good at absorbing moisture, which is a bad thing. So last time I had a lot of trouble getting it in the loaded. What I ended up doing, I'll show it on this. This is not TPU, but it's stuck in there. So what I ended up doing, it's very dizzy, is I did this kind of cut. This is what I normally do with PLA, is make a really sharp point there. That was not working with the flexible stuff. So what I ended up doing is I also cut from the other direction and made more like a cone there. Not a cone, but a point from both sides, so that whichever side of the hole it hit, it would probably go down in there. And that's how I ended up getting it to finally load. In fact, like when I turned the video off yesterday, I did that, and it was 30 seconds later I had it loaded. Now it still didn't print very well. You know, it still have issues printing, but it loaded right away after that. So let's just look. I thought what I would do is I get these samples. These are from MakerBox, I think is the name. I'll see if I can find it. Let's see. Yeah, this is it. I get these. Some from Box Mountain is the new company. MakerBox. They have others, like you can get dice every month. I don't know what's in this one. Oh, these are like the puzzles, or just curated package of stuff. All right, so cryptozoology and paranormal, a dice box, and a filament box. So what this one does is it just every month you get 4 or 5 16-ish meter rolls of filament. All right, and it's $19 a month. A whole spool of filament is about $19, $20 or more dollars. So it's not a great deal as far as the filament you're going to get, but it lets you sample a whole bunch of stuff that you can't buy a whole, or doesn't make sense to buy a whole roll of it, and then turned out that you can't print that, or it's not as what you thought it was going to be, or whatever. So you get these little samples. So I do that, and I'll just go through some of them that I've got, and we'll try printing. I'll maybe try printing some of them today, but we'll go through them and just so you can see some of the stuff that's out there. This one could be cool. This is Pla Thermochromatics. That means heat color changing. And the only problem is that it's not very interesting colors. So I assume there's some better of these. Now it says it will change color with the heat of your hands, which it will do, but not a lot. So I may have to go over to the heat gun back there and actually get it to change color. I mean, you can see it's changing a little bit, but this one just basically goes from gray to a creamy white color. Let me go make it really change color. So, see, that's kind of So if there were more interesting color differences here, then that would be kind of interesting. You could use this for, I don't know, some sort of indicator. Maybe this, I don't know, it says it changes color at 90 degrees Fahrenheit, 31 Celsius. So those are kind of interesting points because PLA generally is going to start warping on you, heat deflecting at around 60 degrees Celsius. So if it's changing color, then you know you're halfway there. It'd be a little bit more useful as an indicator if it changed around 50 or something, because now you'd know that you're about to reach the point of heat deflection. But I guess 30 is also good because that would tell you that, hey, you're halfway to having too much heat on this thing. But it does change color. This particular one's not interesting colors. And it does take a lot more heat than just holding it. So put it in your car or something like that, and it should change color. It will change color just by holding it, but it's just very gradual. You know, you can kind of see where it's changing color there, but you can make it change a lot. All right, so that's that. It prints like PLA. I'll print some of it, just regular stuff like cubes or whatever. Again, these are older ones. PLA is not so bad at being not printable after being stored in a bag like this, so I'm not too worried about it. If you want to test PLA to see if it's going to be a problem, just take the end and bend it a little bit, and if it snaps, then it's probably got too much moisture in it. This one's pretty flexible, so I think it's going to print fine. Actually, just holding it there, you can kind of see it changing color. All right, so that's that. I'm trying to put them back in the bags because once they're out of the bags, you don't know what they are unless you happen to remember. So that's that one. Oh, this one's interesting. So this one I do have some larger rolls of. I don't know what happened there. But this is Polysmooth. So this stuff is, well, extremely moisture sensitive. So you need to dry it to prevent stringing. That's probably true because what this stuff does, it prints like PLA. So 190 to 220, bed temperature, room temperature up to 60. Speeds are in the PLA speeds. Cooling is yes. So it's basically you have PLA settings. But the thing that is interesting about this is that you may have heard of vapor smoothing ABS. You put on some acetone, like brush it on or mist it on there, and it will smooth out the surface of ABS. Let me show you some pictures of that. Find a good image of what that looks like. Here's a Pokemon guy that's been vapor smoothed. So see how it's all shiny? You can kind of pick up a couple of layers in there. But this is not that it's wet or got gloss paint on it. There's an owl up here. This is the surface finish now. Here's a bracket that's been vapor smoothed. So ABS will do this. ABS basically melts with acetone. PLA does not. So you have to do something else. PLA also does not sand very well. So it's a tough material to actually try and sand. But this stuff is can be vapor smoothed with IPA, so isopropyl alcohol, which you can. I thought I had some out here. Oh yeah, you can just spray some isopropyl alcohol on there, and it will smooth it out. They actually make a machine, a polisher. Let's see if I can find that. This guy. They make this machine, not cheap. They make this machine that basically mists IPA in this chamber and rotates your little part around, and so it can kind of more evenly distribute the isopropyl alcohol on the surface of your print. So if you want to print PLA, but you want it to be smooth and shiny, then this stuff from Polysmooth, or well, from what's the name of the company? Polymaker, I think is the name of the company. Yeah, polymaker.com. Polysmooth from Polymaker can be an option where you don't have to try and print the ABS stuff. So that's good. I did find some more TPU that's flexible and clear. So I do have some other clear. This one says works best printed slow using a 0.6 nozzle. So I might go back. I am using a 0.6 nozzle with this green stuff that I've got in there that didn't, this stuff that didn't print very well. I may go back, try lowering the temperature, well, not the temperature, the speed, and I might also try lowering the temperature because it does look like there's some issues with heat creep on this, which there shouldn't be, but looks like that's what's happening. So we'll go back and try to print the green a little bit more, and slower, because this one says 25 to 45. So I might go down to like 30 millimeters a second and try to print this stuff. And this one feels basically like the green stuff, but it's clear. I might try printing that also. Here's one that is PLA, but inside of the PLA mixed in with it are sawdust particles, basically. This one is, it doesn't say what wood is in here, but there's different woods that you can find in PLA. This one gives you a little bit of information on how much retraction you can do with direct drive or indirect drive. Indirect drive means the Bowden tube. Prints at PLA temperatures, probably on the slower side. This one's a mimic filament. So this one does not, that's weird. It says wood filled PLA, but then it says without actual wood powder. So, this is one of the foaming. All right, these are interesting. So there's another one of these that's a super lightweight PLA. And what it does is it actually foams up as you print it. I think I have some somewhere I'll have to find. But it's really good if you're trying to print like RC airplanes, things that need to be super lightweight, because once you've got it dialed in, you print it, and once it's heated, the heating causes it to foam up a little bit, and so you can get these really thick layer lines, but there's a lot of air in the layer there, so it's a very lightweight material. So I think that's what they're doing here, except they're using it to make it look kind of like wood. I don't like that they called it wood filled if it has no wood in it. There are some of these that have actual wood particles in them. The ones with wood particles usually need a hardened nozzle eventually, because they're going to eventually abrade your brass nozzle. You would think that wood isn't going to abrade brass, but over time it will. So this one, I kind of do want to print this one because it is one of the foaming ones. I'll see if I can find some of the actual foaming PLA, and because it is useful, it's a useful material if you're trying to print super lightweight stuff. This is looking like it uses the same technology. That's why they gave me this retraction distance. I wondered why they gave me certain retraction distances for it. It's because of the foaming. Oh, here's another TPU. This one's a little bit more flexible. I might try printing this one. It's just solid red. Nothing special about it. It says it's the easiest to print one, though, so we'll try from Ninja Tech Cheetah. It says it has 84% greater impact strength than ABS, because you can imagine that this is going to be very tough material. So I'll try that. It said it's still slower printing. And then I've got this one, just because I saw it and I wanted to print it. Got some glitter filled PLA. It looks like it is printing a little hotter. The bed does need to be on. Speed is pretty normal. This one definitely says that it is abrasive. You can even see it's got particles, glitter particles all in it, and they're going to be abrasive to your nozzle. So hardened nozzle advised. I currently on this printer have the CHT, the nozzle that splits the filament into 3 little individual strands to melt them. That one is not hardened. It does have a coating on it, but it's not hardened. It's a brass nozzle with a nickel coating, which I don't think that's going to do much. That nickel coating is going to do a whole lot to stop abrasion because it's not very thick of a coating. So we'll need to put in a a different nozzle in order to print this without wondering if we're going to eat up the nozzle, or maybe just print it on a printer that already has a hard nozzle on it. So I have those out. I'll print up those and we'll look at them next time. Next time, what I think I want to do Monday is go through and look at this piece of software. So we're on a software kick right now, I guess. But this one, you can get a demo of this one. The demo doesn't let you do too many things, but this one is actually, it has a particular use case. I was hoping they would show you some pictures here, but it doesn't look like they're. Let's see. I want to see if I can find. Okay, here's an idea. So this is a nozzle. I don't know if it probably it says aerospace, so this must be kind of like a rocket nozzle, and it's got this grid overlaid on the surface of it. So that grid could be there for stress distribution. Maybe this is a ceramic nozzle, and that's for keeping this. It's printed. And that grid keeps the ceramic from cracking when you go to center it. I can't think of the word. Fire it. But this grid is pretty difficult to make by hand to make it conform to a surface that is not flat. And this software in Topology does that kind of thing very well. It has a completely different workflow from stuff you've seen before, so that's why I kind of wanted to show it. It's very much procedural. So you tell it, hey, I want to take this surface and apply this mathematical function to it, and that will generate something like this pattern on the surface here. See if it has some other. What's the medical example look like? So here. This looks like this looks like it's meant. Oh, I can't rotate it around. It looks like it's meant to be a insert for, I don't know, maybe between your knee. I can't tell what they're doing here, but it's got all this lattice work in here, Veronal pattern lattice work type stuff, so that bone probably can ingrow into this. This might be a spinal spacer. I'm not sure. It doesn't have a hole in it, though, to get it in there. So I'm not exactly sure what this particular thing does. It looks like it's supposed to go between two bones and kind of lock in place. I just don't know what. But this kind of geometry would be very hard to generate, but that's what this in Topology does. So we'll run through some of how it works because it works so differently. You can get a demo, like it says here, and I am able to get a full version of it for educational purposes. I don't know if students can, but you can ask them, and it's not it's a request a quote thing, so it's not a cheap thing. So it would be something that you would see in industry. It also has applications for maybe pattern making. Let's see if there's maybe in the automotive industry. Let's see what they have there. Oh no, they're just kind of doing the same thing on this heat exchanger. What else? They have which one other? Consumer products. Fixturing, jig making, that kind of stuff. This one doesn't have a picture with it. But there's some of the consumer products they work with. Oh, there's a picture of concept design for something. But we'll look at this software and our printed parts on Monday. All right. We'll see y'all next week.